Hello, discrete math fans. So induction can also be used to prove inequalities. We just got done with divisibility. Now let's try inequalities. All right, here is an example. Let's find all values of n in the natural numbers so that 2 to the n is less than n factorial. Now from your experimentations in studying infinite series in Calculus 2, you should know that factorials always grow faster than exponentials. We want to find out where this happens. Let's just experiment with a few values. So what I did was I made a table that shows values of 2 to the n and values of n factorial. One of the things that you should notice is that early on the values of 2 to the n are bigger, but eventually the values of n factorial become bigger. In fact, there is this breakpoint right here where it appears that everything beyond there, n factorial, is larger. This is not a proof, but it leads us to think that maybe this is a possibility. It looks like n factorial is starting to get big. So we can make a conjecture on the basis of this evidence that 2 to the n is smaller than n factorial as long as n is larger than or equal to 4. Let's prove exactly this statement. So our theorem is that 2 to the n is less than n factorial for all n greater than or equal to 4. It doesn't work when n is equal to 1, 2, or 3. So for our proof, let's let p of n be the predicate. 2 to the n is less than n factorial. Now let's start with our basis step, and we're going to start at 4 because the theorem is stated to say that this inequality is only going to work when n is bigger than or equal to 4. So since 2 to the 4th is in fact smaller than 4 factorial, right? 2 to the 4th is 16 and 4 factorial is 24. That tells us that p of 4 is true. Now let's let n be a natural number as long as n is bigger than or equal to 4, and let's assume that p of n is true. That is, let's assume that 2 to the n is less than n factorial for this particular but arbitrarily chosen value of n. Now we want to prove that 2 to the n plus 1 is less than n plus 1 factorial. And we're going to leverage what we know, which is 2 to the n is less than n factorial, to try to prove this. All right, so 2 to the n plus 1 is equal to 2 times 2 to the n. But what do we know about 2 to the n? It's smaller than n factorial. So this is smaller than this. That's by our inductive hypothesis. And that's why I've put a little star over the inequality. Your inductive hypothesis does not need to be an equation. In this case, the inductive hypothesis is an inequality. Now we know that n is bigger than or equal to 4, so certainly 2 is smaller than n plus 1. And so now, if we have n factorial times n plus 1, that gets grouped together as n plus 1 factorial. Just peeling off the last term is what's going on there. So that tells us that p of n plus 1 is true, and then by the principle of mathematical induction, p of n is true for all n bigger than or equal to 4. And that's the end of the proof. Okay, that's all for now.